This video is on the equilibrium constant. So the equilibrium constant is what we call K sub C, so Kc. So if we look at this reaction here, we've got nitrogen plus hydrogen makes, oops, and I got cut off there, ammonia, NH3. All right, and you can see it's got that equilibrium arrow. So what that means is this can be a forward reaction and it can be a reverse reaction. And equilibrium is when your concentrations are constant. So you're not going to have equals of like nitrogen and hydrogen on the reactant side with equal amounts of ammonia on the product side. What you're going to have is you're going to have, like, for example, a concentration of ammonia on the product side that doesn't change, that stays the same as it is. So it's same to itself, not same to something on the other side. All right, so no matter what the starting position of reactants and products, the equilibrium mixture contains the same relative concentrations of reactants and products. Equilibrium, so that where it stays constant, can be reached from either direction, meaning it can be forwards to get to that balanced equilibrium, or it can be the reverse. It can go either way to balance it out. We express the relationship between the reactants and products of equilibrium in any reaction like this. So let's say we have this kind of generic letters reaction. So my A reactants are going to be my A and B. Okay, and products are going to be C and D. So even though it can go either way, we always talk about things on the left side as reactants and things on the right side as products. And yes, you could flip it around, but then when it's written the other way, we would say the same, left reactants, right are products. The M, N, X, and Y, those are our coefficients. All right, so an equilibrium expression, actually I think that's, oops, sorry, down here. Okay, equilibrium expression would be Kc equals, it's going to be your product concentrations over your reactant concentrations. Okay, so another way to say this is, and more specifically is, if we have our reaction here, it would be our concentration of C to the X power times concentration of D to the to the Y power. All divided by our concentration of A to the M power and B to the N power. So you can see our coefficients become our exponents, and we are still looking at concentrations. So this right here is our equilibrium constant expression. Okay, equilibrium expression right here. So we're looking at a concentration of products over a concentration of reactants. All right, so concentration, quick reminder, is measured in moles per decimeter cubed. Equilibrium depends on the stoichiometry, not the mechanism. So the mechanism was what we did with rates, right? It wasn't necessarily a coefficient that became your exponent. It depended on the mechanisms, like how it happened. Equilibrium is simpler in that your coefficient is your exponent. Kc is an equilibrium constant that is based on concentration. It does change with temperature, which we'll talk more about later. And the units are generally omitted, so we don't usually just write any units. It's just a numeric value. So let's do a couple kind of practice expressions. So if I've got this one that I started with in the beginning, right? Kc would be my product, so concentration of NH3 squared over my concentration of N2, right? No exponent, so just leave it, right, to the first, and a concentration of H2 to the third. All right, so let's do the second one. And if you want, I'd pause it and try it before, oops, there was one last thing I meant to write. You could pause it and try it before I go over it, but let's go back to here. One more thing I forgot to mention is down here, Kc, when you're doing your equilibrium expression, you're only going to include gases and aqueous solutions. And the reason is gases and aqueous solutions will change easily, and solids and liquids don't change much. So anything that is a solid or a liquid in your chemical reaction will not be included in your equilibrium expression. So maybe let's go back to here and let's do B together. Because what I can see is that they are all gases except for the liquid water. So this is not going to be in my expression. So Kc is now going to equal my concentration of NO2 to the fourth divided by my concentration of ammonia to the fourth and my concentration of O2 to the seventh. All right, so now let's do some actual calculations with this. So given this reaction here, all right, my Kc, I'm going to write that down right here, is going to be my N2O4 concentration over my NO2 concentration squared. All right, so it says when 0.1 moles of NO2 is added to a 1 liter flask at 25 Celsius, the concentration changes so that at equilibrium, these are our concentrations. Okay, so this was at the start, right, before it actually reacted. So what's the value of Kc before any reaction occurs? Well, Kc before anything happens, we have no product, right? We just have NO2. That is added to the flask. So the top is 0. So no matter what the bottom is, which is 0.1 squared, right, it's going to be 0. Okay, so then what is Kc at equilibrium? Well, let's plug in our concentration values there. So Kc is going to be our N2O4, our product, 0.42, divided by our reactant, 0.016 squared. So you type this in, and your calculator is going to tell you it's 1.6 times 10 to the third, with no units for your Kc. All right, so what does this mean? All right, so the last piece of this Kc thing is this. The magnitude is a measure of the yield of a reversible reaction. So, two big takeaways. A large Kc right here, and by large we mean like much greater than 1. So like the one we just had, that would be a large Kc. Means that equilibrium is going to be attained by shifting right, meaning you're going to be making more products, right? Right would be making more products. So reactants are going to be turning into products to get that to be at equilibrium. If you have a really small Kc, it's the reverse. So much less than 1, it's not going to be negative, right? You can't have negative concentration. So it's going to be like 0.0 something. Your equilibrium shifts left. So you're going to have products that turn into reactants. Now, if you think about this, remember Kc is product concentrations over reactant concentrations. This should make sense. If Kc is much bigger than 1, that means your numerator value, your product value, would have to be bigger, a lot bigger than your reactant, your denominator. And then a small Kc would be when you have a fraction that's much less than 1. That would be when your reactants are bigger than your products. And that's the direction they're shifting in. So that is the equilibrium constant.